Hi everyone, so let's see what we are going to study in this lecture. So what we have already studied till now, we have studied diode. So what was diode? Diode was a two-terminal device. Diode was two-terminal device. Why two-terminal? Because this was the structure of diode. Two-terminal device, this is first one, this is second one. Diode was a two-terminal device. So in two-terminal device, we saw different application. First we saw clipper circuit. What was clipper circuit? Clipper circuit clips of the undesired part of the input signal. What does clamper circuit do? It sets a new DC level. That means it clamps up or clamps down the input signal. What does peak detector do? Detects the peak value, positive or negative. So in the output you are having some DC value. It can be plus Vm or minus Vm. In clamper you are having AC plus DC, but AC was not amplified. AC was remaining as it is. Vm sin omega t was there. Just the DC level was shifted, plus Vm or minus Vm. In clipper, the waveform was getting changed, but it was not being amplified. What was voltage multiplier? In voltage multiplier, the voltage was getting amplified, but your output was DC. Assume my input is Vm sin omega t, so at the output you can have 2 Vm, 3 Vm, 4 Vm, but the output was DC only, not AC. So these were the application we saw. So using the diode circuit, let's assume if this is my input Vm sin omega t, and if I want my output to be 2 Vm sin omega t, can you do that using diode circuit? Can you do that using diode circuit? No, right? We can't do that using diode circuit. We tried doing it. When we tried doing it, what happened? We tried doing it with the small signal analysis. When in small signal analysis, when diode is on, we replaced it with RD equals to neta Vt upon IDC. In the initial lectures, we saw that. And when it was off, we replaced the diode with open circuit. So let's assume, based on the DC analysis, if diode is on, if diode was on, if diode is on, what would be your output? Your output would simply be some DC output plus what would have happened to AC. For AC, this would have replaced with RD, so your output would be RD upon RD plus R into VAC. So this is not amplified, right? Let's assume RD is 2 and small RD is like small RD is 2 and capital R is 5. So it would be 2 upon 2 plus 5 into Vin. So 2 Vin is VAC actually. So 2 by 7 VAC. This is not amplified, right? You are not getting the amplification here. And if it was off, then what would have happened? If diode is off, what you would get? You would get simply V naught would be equals to VDC plus VAC. So again, it is not amplified. So you are not getting an amplified output, not getting amplified output from diode. We are actually moving to our 4-terminal device or 3-terminal device. So why do we need that device? This is what I am telling here. So not getting amplified output. So because of that, yeah, so this is what I have written here, Vm sin omega t. So using diode circuit, let's assume I want k Vm sin omega t, where k is greater than 1. So this is not possible. Mod of k is greater than 1, I would say, because it could be minus 2 Vm sin omega t as well. That is also amplified, just the phase is changed. So this is not possible. Not possible. I can put a cross mark. This is not possible. So you need a 3 or 4 terminal device now for the amplification of the input AC signal. So now we need a 2 terminal, not a 2 terminal, but a 3 or 4 terminal device. So let's assume this I am calling as terminal 1, terminal 1. This is terminal 2. This is terminal 3. And this is terminal 4. Terminal 4. Okay. And this terminal 1 will be the, one of the terminal would be the controlling one. So I am writing it as a controlling terminal. So one of the terminal will be controlling one. That it will control the current. One of the terminal will control the current. So what is a basic amplifier? What is a basic amplifier? In basic amplifier, what do we do? It can have some input resistance. So this is a basic amplifier. So in the amplifier is a black box. Okay, just assume it is a box. So in amplifier, what do? You give an input. This is your black box. This is your black box. Amplifier is a black box. It can have some output resistance as well. Amplifier can have some output resistance R0 as well. So you give some input. It amplifies the input. It can change it into current as well. It can change it into voltage as well. We are assuming it is changing our input voltage into current with some factor K. So it has changed our input voltage in current, and then at the load we are having some resistance RL. So what will be your output? So your output is K into RL into Vin and a negative sign. So basically your output is amplified by this. Now you have the control over RL, you have the control over K. So based on the control K and RL, you can have an amplified output. What did we do? This is an amplifier. This is an amplifier. In the amplifier, at one port we give the input. That input is amplified into a current. That voltage input is changed into a current, and that is going towards the output. So at the output we are having minus K into RL into Vin. You have the control over RL, you have the control over K. So from here you can get the amplified output. So here we can get amplification, and this is what we needed. So this kind of amplifier can be made using 3-terminal or 4-terminal devices. 3-terminal devices BJT, bipolar junction transistor, and 4-terminal devices JFET and MOSFET. MOSFET is metal oxide semiconductor field effect transistor. So we will study one by one. First we will study MOSFETs. So MOSFET is a 4-terminal device. So first we are going to study about field effect transistor. So in field effect transistor there can be other devices as well, JFET, MOSFET and other FET as well. But we have to study about MOSFET only, because this is the only important and most important part. We will study about MOSFETs. So what does MOSFET stand for? Metal oxide semiconductor, and FET stands for field effect transistor. We will understand the meaning of every term here. Why metal, why oxide, why semiconductor, why field effect transistor. We will understand the meaning of every single term. Before that, let's do the classification. So MOSFET are of two types. What are the two types? NMOS, PMOS? No. They are of two types, and these are depletion type MOSFET. Depletion type MOSFET. And the other one is enhancement type MOSFET. And these are classified into two further parts, that is N type and P type. So this can be N type, P type, N type, P type. So we will study one by one. First we will study N type depletion MOSFET. Okay, N type depletion MOSFET. This is what we are going to study. So first we will see a general structure of a MOS, which is of N type. So in N type, what we are having here, we are having N well. What did I say? N well. That means you are having N type of semiconductor here. This is what you can consider. This is N type. This is also N type. This particular node is known as source, and this particular node is known as drain. What does they do? Everything we are going to study. What are they going to do? Everything we will study. And then there is a N channel there. So in depletion type of MOSFET, the channel is already present. What I am going to write, the channel is already present. In depletion type MOSFET, channel is already present. The N channel is already there. So this is how a MOSFET looks. This photo I got from ResearchGate's website. So this is how a MOSFET looks. So this I have drawn source here, drain here. So this is the front view, and at the top what you will see, this layer, and then this layer, and then this box. This is what you will see from the top layer. So this one, this layer, this particular layer is the metal. Then you are having an oxide, and then you are having a semiconductor. This is a P type of substrate, so the P semiconductor is there. In P type of substrate, there are N plus, and N channel. So you had a P type of substrate, and there you put N plus, and N channel. Then on that particular substrate, you are having oxide and metal. This N plus you are calling source, then N plus you are calling drain, and over the metal you are calling that gate. Here you will pick one node that you are calling gate. Here you will pick one node that you are calling source. Here you will pick one node that you are calling drain. Understood? This much of concept you understood? This length is known as L. This is length, and if it is backward, it is width. Length and width. You can see it in the diagram, length and width. So this I don't need to show here. So everything is clear. Metal oxide semiconductor. That's why we call it MOS. Metal oxide semiconductor. Why it is called FATE, that we will also see. And this particular node is known as gate, drain, and source. Now what do they do? What are the definition of source, gate, and drain? Let's see that. Let's see that one by one. So what is the source? Okay, the screen is going black. Let's wait for a second. Yeah, it's fine now. So what is source? So source supplies the charge carrier to the channel. What does drain do? Drain collects the charge carrier from the channel. And what does gate do? Gate controls the flow of charge carrier. These are the three things. Okay, first thing is that it is 4-terminal device. So there are gate, source, and drain. There is this body terminal as well. What is the use of this body? We will see that. In the later part of the video, we will see that what is the use of this body. So there are 4 terminals: source, gate, and drain, and body. So source, drain, and gate. Source, from here you will get the charge carrier. It will travel through channel and it will be going out of drain. That's it. From N plus you will get the charge carrier. It will travel through the channel and will be going out of the drain. Let's understand it with the analogy. That is this analogy. So it is like a tap. In tap, if you turn it on, what happens? Water flows from some source. From some source, water comes and then it flows and gets out of the tap. So this particular space is source, from where water is coming. Then there is a channel for water to flow, and from the drain it will get out. And gate will control the flow of the water. So similarly, here the gate will control the flow of the charge carrier. If you increase the gate voltage, if you decrease the gate voltage, something can happen. If you increase it, your current can increase. If you decrease it, your current can decrease, or current can be zero as well. So based on the potential of gate, the flow of charge carrier is maintained. So did you understand all the point here? From source you are getting the charge carriers, then from channel it travels, and from drain it gets out. And gate controls the flow of the charge carrier. Now why it is called FET? Field effect transistor. Field effect transistor. So the flow of current is modulated because of the applied electrical field or applied voltage. So here you will apply some voltage at drain, at source you will apply some voltages. Because of that, the flow of current is modulated. That means because of the applied voltage only you are getting some current. So this particular transistor is running in the effect of a field, that is electrical field. So this particular transistor is running in the effect of the electric field. That's why it is called field effect transistor. So did you understand the complete meaning of MOSFET now? Metal oxide semiconductor, field effect transistor. Metal oxide semiconductor, and this particular transistor is running in the effect of electrical field. So that's why it is called field effect transistor. So MOSFET, metal oxide semiconductor, field effect transistor. So did you understand the meaning of MOSFET now? And what is the source, what is the gate, what is the drain, and what is the channel? So I hope you understood the meaning of MOSFET. Now we will see what is particularly N-type depletion MOSFET. So what does this define? Type. That means this defines the channel, that your channel will be of N-type. So here your channel is of N-type. So we will call it N-type depletion MOSFET. And if it is P-type, your channel will be of P channel, right? Your channel will be of P type. So here the channel is already framed. Now what we will do, we will apply some voltage on gate, drain and source. Then we will see what happens in this particular device. Okay, so first condition we are taking that my VGS is 0 and VDS is positive. Now I will tell you one thing. In the complete analogy, not analogy, in the complete lecture, what we will do, we will always take source as a reference. We will always take source as a reference. That means we will keep it grounded. If I am saying that I am applying VDS to be 4 volt, that means I am applying drain voltage to be 4 volt. It's not that I will apply 3 volt here and minus 1 volt here. This is you can do. But for better understanding what we are going to do, we will take source as a reference. Okay. We will always take source as a reference in the complete lecture. Source will be at reference. That means source will be shorted. So if I am saying that I am applying VDS to be positive, that means here I am applying positive supply. If I am saying VGS is negative, that means this is also shorted. And one more thing, until I explain you body effect, there is a phenomena that is known as body effect. So until I explain you body effect, till that time source and body will be shorted. Till that time source and body will be always shorted. If I forget to show it shorted, you have to assume it. Source and body will be always shorted until I explain you the phenomena named body effect. So source and body are shorted. So this is grounded, and since they are shorted, this will also be grounded. So this is also grounded. So source and body are grounded. Now here I am saying that VGS is 0. That's why I put a gate voltage also 0. And now I am saying that VDS is positive. That means at drain I am applying positive supply. Now what will happen if I apply positive supply at drain? If I apply positive supply at drain, what will happen? Let's check that. So yeah, before checking that, let's get the meaning of N plus. What do you mean by N plus? Plus means it is highly doped, and highly doped means more conductivity. By the way, what is N-type semiconductor? This is N-type semiconductor. I hope you remember it because in the initial lecture we have studied it. This is N-type, right? And what is P-type? P-type is this. In N-type we get electrons, and P-type we get holes. In the initial lecture only we have studied it in the diode circuit. So N plus means highly doped, that means more conductivity. More conductivity means lesser resistance. Less resistance. And N is lightly doped. Lightly doped means less conductivity. That means more resistance. So if I am saying that this is my source, this is my drain, this is my channel, this is N plus, this is also N plus, and this is N. So this particular region is having more resistance, right? This particular region is having more resistance, and N plus are having lesser resistance. So what I can do, I can replace, just as a analogy, what I can do, I can replace this something like this. This source, channel and drain, I am replacing it something like this. This I can call source resistance. This I can call channel resistance, and this I can call drain resistance. So here channel resistance is the maximum. Here channel resistance is more than drain and source resistance. Why so? Because it is less doped. Less doped means it is having less conductivity. That is, it is having more resistance. Now tell me one thing. What did I say? That I am applying positive voltage here. What did I say? I am applying positive voltage here. Let's assume if I apply 8 volt here. If I apply 8 voltage here, what will happen? For better understanding, I am assuming that this R channel is double of R drain and R source. This is my assumption. Assumption is that this R channel is double of R drain and double of R source. So if I am applying 8 volt here, what will happen? 2 volt will be coming here, 4 volt will be coming here, and 2 volt will be coming here. More voltage, sorry, more resistance, more voltage. If it is having more resistance, that means it will take up more voltage, although the R channel will be more than the double. So the point here is that if I apply some voltage here, let's assume I am applying 10 volt here, so most of the potential will be coming across the channel itself. Are you understanding this point? Since the channel is having lesser conductivity, that means it is having more resistance, so whatever the potential I am applying at the drain side, most part of that potential is coming across the channel only. Are you agreeing to this point? Say yes or no. And this potential is linearly divided, like here 8 volt, then here 6 volt, then here 2 volt, and here 0 volt. So 8 volt, 6 volt, then in between this resistance somewhere 5 volt, 4 volt, 3 volt, 2 volt, 1 volt, then 0 volt. So this is linearly divided. So 8 volt I am applying here, that 8 volt will be linearly divided in drain, channel, and source. If you have already studied this MOS physics, then you might not have studied it in this manner. I know, like most of the place, what I have seen, that they will say that here you are applying positive voltage, so positive will attract the electrons, so current will flow. This is not the region. Okay, in one of the short video you will find this region only, that how the current flows in n channel depletion type MOSFET. If you apply positive voltage, this electron will be attracted by this positive supply and current will flow. But that is not the correct region. Slowly we are moving towards the correct region. Okay, in the interview if you say these kind of things, they will reject you. So this we have understood. Now what we are doing, we are applying the positive voltage at drain terminal. So here we are applying positive voltage. Now see the structure of MOS. What you can see, this is P substrate, right? And these are N. P substrate and all are N. Can you assume a diode here? Look, diode is not practically there. It's not that diode is practically there, but we can assume a diode kind of structure. We can assume that a diode kind of structure, right? So basically, oh, not this P substrate. This I had to remove. Yeah. So I'm breaking this R channel. Okay, I'm breaking this R channel in two parts. This is my R channel only. This is R channel. This I have broken into two parts, and this is R drain. And here I am applying some positive voltage. Let's say that is 8 volt. Now at each side, what I am seeing, I will see a PN junction kind of structure. Here there will be again PN diode. These will be the PN diodes there. Now 8 volt is there. Now 8 volt will be linearly divided. What will come here? 6 volt. What will come here? 4 volt. What will come here? 2 volt. Now this potential, whatever the potential it is, it would be equal only, right? Let's assume everywhere the potential is X. Everywhere the potential is X only. And this 8 volt is linearly divided. So 8 volt, 6 volt, 4 volt, and 2 volt. Tell me one thing, which diode is having the maximum reverse bias? This one. Maximum reverse bias. And this is having the minimum reverse bias, right? So what did you understand by this point? in the MOSFET, if I am applying in the N channel MOSFET, if I am applying a positive supply at the drain side, then from drain to source, the reverse bias is getting decreased. If I am applying a positive potential at drain side, from drain to source, the reverse bias is getting decreased. So here this diode has the maximum reverse bias. And also most of the potential are there across these diodes only. So here in this region we are having the maximum reverse bias, but slowly the reverse bias is getting decreased. If reverse bias is getting decreased, that means the depletion region is also getting decreased. If you remember PN junction, that's why I said that PN junction is very important. So more the reverse bias, more the depletion region. If I increase the reverse bias, this region would have increased. So more the reverse bias, more the depletion region. So what I can write, from drain to source, reverse bias decreases. That means depletion width decreases. So at the drain side you will have the maximum depletion region, and at the source side you will have the minimum depletion region. So this is how your depletion region would look like, and this is I have drawn channel. So this is not a complete MOSFET. This is these two part only. These two part only I have drawn. Channel and the drain. This is the drain. This is the channel. So, and what is this? What is this? This negative, negative, negative. From where this negative is coming? That is P substrate. This is P substrate. P substrate. This is P substrate. So now what is happening? At the drain side we are having reverse bias. So there is this depletion region. Because of this depletion region, there is this electric field is generated. Because of this depletion region, electric field is generated. This you can't see. You can use green color pen. So because of this depletion region, plus and minus, there is electric field generated. Now this, what will this electric field do? This electric field will attract these electrons and will make them travel in the opposite direction of electric field. So these electrons will be swept away in the drain region and will get out of there. So this was the region. This was the actual region why the current flows. When I apply a positive bias at the drain side, what happens? Depletion region is formed. Because of this depletion region, there is high electric field there. Because of this electric field, the electrons in the free electrons in the channel feels the attraction in the electric field and it is swept to the drain terminal. The electron moves in the opposite direction of the electric field and swept away from the drain terminal and the current flows. Are you getting this point? So these electrons are getting swept away in this direction. So very crude way was that because of this positive supply, here there are electrons, they are getting swept. But what is the other reason is the actual reason is that this is the bias is framed, this electric field is framed, right? This electric field is framed because of the depletion region. This electric field is framed. Oh, sorry. Yeah, this electric field is framed which has this direction. And plus, wait a second. Just a minute. Yeah, electric field have this direction. Sorry. Yeah. So this electric field is framed. The direction is this. And since there are some free electrons here, because of this electric field, they are getting swept away in the drain side. Because electron will travel in the opposite direction of the electric field and they will be swept away from the drain terminal and the current flows. Are you understanding this point? Right? Well and good. So this is what is happening here. And one more thing is happening, that because of this positive supply, this here this is increasing. Look, this is p type and this is, sorry, this is n type and this is p type. If I am applying positive potential here, what is happening? Most of the positive potential is coming on this side. Because of that, this is n and here it is p. Because of that, this depletion region is increasing. What will happen if I keep on increasing VDS? If I keep on increasing VDS, what will happen? The depletion region will keep on increasing from drain side. From drain side, the depletion region will keep on increasing, because at the drain side maximum potential is there. Then slowly the potential is decreasing. So at the drain side you have the maximum potential, then lower potential, then lower, then lower, then more lower. So at the drain side, the depletion region will keep on increasing. So what will happen? If I keep on increasing VDS, what's going to happen? It will be somewhat like this, right? And the rest of the areas, this rest of the area will be plus only. Here if I am making this one, what do I mean? I mean this. But here only I am showing the electrons. So slowly, here this part, channel is getting depleted of charge carriers. If I am increasing VDS value, more positive potential will be coming on the channel. Because of that, the channel is getting depleted of charge carriers. Positive potential, that means reverse bias. Reverse bias means depletion region is increasing. So depletion width is increasing. If I increase more, what will happen? If I increase more, then depletion width will increase more. But what is happening? Since this positive potential at the drain, I am applying this positive potential, the electric field is getting strong. If I am increasing VDS, the electric field is getting strong. That will attract these electrons very fastly. So the current will increase. But that will happen initially only. Initially, I am increasing VDS. So what is happening? The depletion width is getting increased. If depletion width is getting increased, that means this particular electric field is getting strong. If this is getting strong, that means it is attracting those charge carriers very quickly. But at a certain time, at a certain VDS, what will happen? At a certain VDS, this channel will start getting depleted of charge carriers. Here the charge carriers will be very less. Although the field is very strong, but charge carrier is less only. So the current will saturate. Did you understand this point or not? My VGS is 0. I am not talking about VGS. What I am doing, I am increasing my drain potential. If I am increasing my drain potential, what did I get to know? That most of the potential will come across the channel itself. That means there will be a reverse bias. So because of the reverse bias, there will be a depletion region, and in the depletion region, there will be electric field. What this electric field will do? This electric field will attract these electrons, and if attract these electrons, the current will flow. If I keep on increasing the drain potential, what is going to happen? If I keep on increasing the drain potential, the electric field will be stronger and it will attract the electrons more. It will attract the electrons fastly and the current will increase. But at a certain VDS value, what's going to happen? In the channel, there will be very less charge carriers. Although the field is strong, electric field is very strong, but still there are lesser charge carriers, and because of that, the current saturates. So this is the complete concept of N-type, N-channel depletion type MOSFET. Did I write N-type there? When I showed the classification, I guess I write N-type. N-type. Oh, look, this should be N-channel. Shouldn't be N-type. N-channel. So this 30 minutes of this video was the most important part. If you are able to understand this 30 minutes, rest 2 hours or 2.5 hours will be very easy for you. This is the most important part only. So here I explained you what is MOSFET, why it is called MOSFET, metal oxide semiconductor field effect transistor. What is the meaning of the source, drain, gate and channel? What is the meaning of FET? then I showed you this analogy, then I told you what will happen if I apply positive potential at the drain. So what will happen? So first we understood this analogy that this can be replaced with the resistance. R channel is the higher resistance, R drain is the lower resistance. So if I am giving 8 volt here, the most of the potential will be coming towards the channel only. So because of that, here we can see that there is a PN diode there. So now all the diodes are reverse bias. Because of the reverse bias, there will be depletion region. Now if I am giving positive supply at the drain, that depletion region will induce an electric field. So because of that electric field, the electrons are swept away in that drain terminal and the current flows. If I keep on increasing the VDS value, what will happen? The electric field will be stronger and that will attract the electrons fastly and current will increase. But at a certain value of VDS, the channel will be, I will not say that channel will be depleted of charge carriers. I will say that in the channel there will be less charge carriers. Although the electric field is strong, but charge carriers are low only. So that is the reason why the current saturates. That's it. That's the complete concept. I hope you are able to understand. Now we are going to write everything that we have said. So what if I increase VDS? So now what first thing I should write is that VDS is positive, then uh, electric field E is generated. E will sweep away the electrons in drain terminal. And the current flows. What will be the direction of current? Electrons are going in this direction. From source they are coming from the channel and then they are going to drain. Electrons are going in this direction. Then what will be the direction of current? The direction of current will be from drain to source. Because the direction of current is always opposite to the motion of electrons. Electrons are moving from drain to source. Sorry, from source to drain. From source to drain. So the current will flow from drain to source. Now what if I increase VDS? If I keep on increasing the VDS, that electric field E will be stronger, electrons will travel fast and the current increases, right? But the current increases, but the saturation level I did not explain, no? So here I will explain the saturation level. So here the current will increase, but after a certain value of VDS, the current saturates. So here I will write about the saturation. But at a certain value of VDS, the channel will start having very less charge carriers. Although the field is although the electrical field is strong, but the charge carriers are less. Charge carriers are less, and because of that current saturates. that current saturates. Okay, and this all was happening at VGS equals to 0. So first it increases and then it saturates. So at this potential it saturates. This potential is known as VD set, VDS set. Okay, and this is known as IDSS, saturation voltage, saturation current. I generally write it as ID set. ID set. Well and good. Now we have seen the effect of VDS and increasing VDS. Now we will see the effect of VGS. What will happen if I apply VGS? So now VDS is positive, that is there, that I can call, that is fixed. Now I will vary my VGS from negative potential. I can vary my VGS from -5 to +5, and I will see how what happens. Initially there was no VGS, VGS was 0, but now I am varying my VGS from -5 to +5. So what happens, that I will see. So now my VGS is negative. So this is negative, and this I have made channel only. So this negative, this will repel the electrons. This will repel the electrons. Or for better understanding, I should make something like this. Why this is grounded? This should not be grounded. This is channel only, right? So I am giving a negative supply. That means I can make a battery something like this. Now where will this node go? This node will go to body. I am connecting the supply here like this. This is what I am doing. I am connecting the supply like this. Understood? So what is happening? What this will do? This is the positive side. This is the positive side. So what this will do? This will supply holes. So this holes will first get into the substrate. Then it will go to the channel, right? Or what you can see that because of this positive supply, the holes in the substrate, this is the substrate, the holes in the substrate will be repelled by this positive supply. So they will go into the channel and will recombine with these holes. So these holes will be, recombine with the electrons, and these electrons will be eradicated from there. So if you are giving the negative supply at the gate terminal, what is happening? Your channel is getting depleted of charge carriers. What you can see, because of this negative supply, what you can see that these are getting repelled. This is one analogy. This is one way of understanding it. What can be the other way? Other way is that you are applying a battery. So from here, holes are going there, and you can say that positive supply is there, and in the substrate we are having p type. In the substrate we are having p type. So in the p type, these holes will feel the repulsion. So these holes will go into the channel and it will recombine with the holes. And because of that, the channel is getting depleted of charge carriers, and there are less charge carriers. That means there will be lesser current. So current is decreasing. Did you understand this point? Very simple. Negative potential is there. You can see that electrons are getting repelled. This is the one phenomena you can see. Or what can be the other phenomena? That because of the positive supply, the holes are getting repelled. Holes are getting repelled and they are going into the channel. And because of that, the electrons are getting recombined and channel is getting depleted of charge carriers. That's it. So what we can see that if Vg is going down, or I should write, if Vg is increasing in negative direction, what I can write, if Vg is increasing in negative direction. What do I mean by increasing in negative direction? Increasing in negative direction, this is the negative direction. So -1, -2, -3, you will understand, right? Vg is increasing in negative direction. So if Vg increases in negative direction, if Vg is increasing in negative direction, that means what is happening? Vg is increasing in negative direction. The channel is getting depleted of charge carrier. Getting depleted means the charge carriers are getting less. Getting depleted of charge carriers. And what does that means? Current will be decreasing. Current is decreasing. So if gate potential is negative, the current decreases. And what will happen if we keep on decreasing the VGS value? Keep on decreasing the VGS value, what do I mean? That gate potential is increasing in negative direction. That means -3, -4. At some potential, we are just decreasing the negative, we are just decreasing the VGS value. That means we are increasing in negative direction. So we keep on decreasing the VGS value. So if we keep on decreasing the VGS value, then at some negative VGS value, the channel will be depleted of charge carriers, and there will be a very high electric field in the vertical direction. This is the positive supply and this is the negative supply. So what will be the direction of electric field? Yeah, so there is an error in this one, that this should not be there, because to the substrate we are giving the holes, right? This is the supply. So what is the scene? That here we are having the oxide layer. Here we are having the oxide layer, and above that we are having the substrate. Not substrate, we are having the metal, sorry. And here we are giving the supply. So we are giving the supply like this. Negative supply we are giving, and positive supply will be given to the substrate. Here substrate. So we are actually delivering the holes. So this I made here, that is wrong. This should not be happening. So there will be electrical field, but which electric field? Here there is negative potential here. This is the negative potential. This is going towards body only. So let's just write body here. So this is the negative potential, and because of this negative potential, these are getting depleted of charge carriers. So there will be an electric field, that will be this. This will be electric field there. Metal, oxide, and semiconductor. At metal you are having negative, here you are having positive. So there will be this electric field. This electric field will be there. Now what will happen? This source will try to supply electrons. This source will try to supply electrons. The electrons, what will electron try to do? Electron will try to travel from the channel and go towards the drain. But there will be so much of high electric field that just as it enters the channel, it will travel in this direction. The electron wanted to go from source to drain side. The electron wanted to go from source to drain side. Electron came out of source side. Since there was very high electric field, this was the trajectory of electron. This was the trajectory of electrons. Electron wanted to go like this, from source to through channel to drain, but there was so much of high electric field that it goes like that. I will not say that my channel is depleted of charge carriers. At some place I have seen that they say that the channel is depleted of charge carriers, but channel is not depleted of charge carriers. In the channel, charge carriers are there. There can be some charge carriers, but there is so much of high electric field that the motion of electrons will be downward. So the reference of this thing I took from Kamesh sir. There is no harm in taking his name. So just the EDC concept, this is the concept of EDC. So that I took the reference from Kamesh sir. So there is no harm in taking his name. But the concept of analog electronics are mine only, that I framed. So I am not completely copying, I am not blindly copying. This reference I took from him. So the credit goes to him for this kind of concept, or this concept. Rest of the part is mine only. So I'm not just credit should be given to the teacher who has taught this. So I have been one of his students for EDC, not for analog. I haven't studied analog from him, but for EDC I have studied. So from there I am taking this reference. That electron comes and then there is an electric field. So trajectory of electrons will be downward. So the electron doesn't reach the drain terminal. So the current becomes 0. So this is what I have written. At some negative VGS value, the channel will be depleted of charge carriers. I haven't written completely depleted of charge carriers. The channel will be depleted of charge carriers, and the electric field in vertical direction will be so strong that electron from source side will not be reaching towards the drain side. Electron from source side will not be reaching towards the drain side, and the current becomes zero. So even if you have applied positive potential, there is no meaning of this positive potential because electrons are not even reaching there. The positive potential will be useful if the electrons reach there and this positive supply can attract those electrons. But this is not even useful because electrons are not even reaching there because of this very high electric field. Did you understand this point? So if we are decreasing the VGS value, that means if we are increasing the negative supply at gate potential, the current will slowly start decreasing, and at some negative potential, the current will be zero. And this negative potential is known as pinch off. This negative potential is known as pinch off voltage. So this negative potential is known as pinch off voltage. So this is the reference that I have took from Kamesh sir, and rest all the content is mine only. Diode circuit, and further in MOS amplifiers you will study a lot of concepts that are mine only. So that is not taking although those reference I am taking some textbook, Rajavi's textbook I am following Cedra Smith, and I am also following other textbook as well. So from those textbook I am taking those reference. For a particular teacher I took this reference from Kamesh sir only. So that's why I took his name. Okay. Yeah. So negative potential is known as this pinch of voltage. Well and good. Now, what if I am increasing the VGS value now? That means I am giving positive supply to VG. If I am giving positive supply, what will happen? This will attract the electrons, right? It will attract the electrons, and the channel will be, in the channel there will be more charge carriers, and if there is more charge carriers, that means there will be more current flow. Or how you can understand it? You are giving positive supply, and then there will be this body terminal. So from here electron will go, right? Electrons, and they will be going into P substrate, and from P substrate what are there? In P substrate these are there. So first these electrons will recombine with these holes. First these electrons will recombine with these holes. After that some of the electrons will reach here and will enhance the channel. Will enhance the channel with electrons, with free electrons. So in the channel we will have more electrons, and if there are more electrons, that means there will be more current. So from the negative supply, electrons are going there. Some are recombining with the holes, and some are going into the channel, and because of that we are having more electrons in the channel, and the current increases. So what do we say? If Vg is increasing, that means there will be more electrons in channel, and that means the current will increase. If you just understand one device, that means n channel depletion type MOSFET, if you understand, then it will take minimum effort in understanding p channel depletion type, n channel enhancement type, p channel enhancement type. So within 1 hour you will be able to understand everything. Just this part is typical. After that everything will be cakewalk, and I guess I have explained it that much of nicely that you are able to understand. This doesn't seem typical to you. I hope this is not typical to you now. Every concept is crystal clear to you, right? So let's move on to the graph now. This is the characteristics. So first we draw for VGS equals to 0 volt. That first it increases and then saturates. If my VGS is negative, that means the current will be decreasing, and if it is my positive, then that means the current will be increasing. So I could have made this graph, then it would be for VGS equals to 2 volt, right? But we are not making it, just telling you. If I have made this graph, this would have been for VGS equals to minus 2 volt. And at VGS equals to VP, what is happening? The current is 0. At VGS equals to VP, the current is 0. Because there will be so much of negative potential that the channel will be depleted of charge carriers, and electron from source side cannot go towards the drain side. So the current will be 0. Did you understand this complete concept? This curve you understood, right? Initially the current increases and then saturated based on VDS value. This is ID versus VDS curve. So if we keep on increasing VDS, it doesn't mean the current will keep on increasing. Why it saturates? Because the channel will have lesser charge carriers. There will be high electric field, but the charge carriers are less, so the current saturates. And if we are increasing VGS value, then what will happen? The current is increasing, right? Let's draw the ID versus VGS curve. So how will the ID versus VGS curve look like? For this potential, for VGS equals to VP, the current is 0. After that, the current keeps on increasing, right? This is for, let's just say this is for one particular VDS value. Let's call this as VDS1. Now I will make 2 more graphs, and you have to tell me the relation between VDS1, VDS2 and VDS3. This is VDS2 and this is VDS3. So tell me, what is the relation between VDS1, VDS2 and VDS3? VDS3 is more than VDS2. Okay. This should be VDS2 and this should be VDS1. VDS2 and this I can call VDS1. So VDS3 is greater than VDS2 is greater than VDS1. Why so? If you increase VDS, what happens? The current increases, at least till this region. So here one thing I should write, that VDS value is not that much large that the current is saturating. The current is not saturating. The VDS value is such that the current is not saturating. Here VDS1, VDS2 and VDS3 are such that the current is not saturating. So this potential of VGS, at a particular potential of VGS, which current is higher? Let's just assume I am applying VGS equals to 1 volt. This is VGS equals to 1 volt. At VGS equals to 1 volt only, in this curve you are getting this much of current. Let's say this is 5 ampere. In this curve you are getting 3 ampere. In this curve you are getting 1 ampere. So you are getting maximum current in VDS3. That means VDS is highest. Because if you increase VDS, the current increases. At least the current never decreases. If you are increasing VDS, the current is never decreasing. So if at the same potential at 1 volt only, if you are getting more current, that means VDS is higher. Did you understand this? This is simple mathematics. This is the question of mathematics, not the analog electronics or electronic devices. Did you understand it? At the same VGS potential, VGS is same. At that same potential, one of the curve is giving me more current and one of the curve is giving me lesser current. So the curve which is giving me more current, that means there is high VDS. If there is high VDS, that means there will be high depletion region, that means there will be more current. So VDS3 is higher than VDS2 is higher than VDS1. Well and good. So this we have studied completely N-channel depletion type MOSFET. Just by seeing this structure, are you able to comment on the complete N-channel depletion type MOSFET? So in one go only I will comment on complete depletion type of MOSFET. So what happens? First I apply VDS equals to positive voltage. If I apply VDS positive voltage, most of the potential will be going towards the channel only, and the potential will be equally distributed from drain to source. At the drain side you will be having the maximum potential. If you are having the maximum potential, that means there will be the maximum reverse bias between N and P. If there is maximum reverse bias, that means there will be highest depletion region, and the region will keep on decreasing with the moving towards drain to source. And if there is very high depletion region, that means there is very high electric field. So the electrons that are present in the N channel, they feel very high electric field and swept away in that drain terminal. That's why the current increases. If you keep on increasing the drain potential, what will happen? The reverse bias will increase more. That means depletion region will increase more. There will be more electric field and the current will increase. But if you further keep on increasing VDS value, what will happen? The electric field will be so strong, but the channel will be depleted of charge carriers. In the channel, we will have less charge carriers, and because of this less charge carriers, although the field is strong, but the charge carriers are less, so the current saturates. The current will be saturated. So ID versus VDS curve will look something like that. That if we are increasing VDS, the current will increase, but after that the current saturates. Now what about VGS? Now my VD is positive potential, that is fixed. Now I am applying VGS potential. If VGS was 0, even though there was no VGS, still there was some current. Now I am applying VG value to be negative. If I am applying VG value to be negative, what it will do? It will supply the holes to P substrate, and these holes will go towards the channel as well. That will recombine with the electrons. Those holes will recombine with the electrons, and in the channel we will have lesser electrons now. In the channel we are having lesser electrons. So that means our charge carrier is less. Here what is our charge carrier? In this N channel, what is our charge carrier? Charge carriers are electrons. Charge carriers are electrons, not holes. Because electrons travel from like this. Charge carriers are electrons. So charge carrier will be less, and because of that the current is decreasing. So if you keep on decreasing the value of Vg, that means in the negative direction, if you are increasing the Vg potential, that means more negative Vg, lesser current. So if Vg is more negative, that means the current is lesser. If Vg is more positive, that means it will provide electrons to P substrate, and that will come into the channel. So that will increase our charge carriers, and because of that the current increases. So this is the complete concept of N channel depletion type MOSFET. Crystal clear? Now you can comment on P channel depletion type MOSFET on your own. Tell me one thing, what will be the charge carrier in P type? In P channel depletion type MOSFET, what will be the charge carriers? Holes, right? Holes will be coming out of here and it will travel like this. What should be the potential at drain? In the N channel, what was the potential at drain? Positive. The potential at drain was positive. Source will always be shorted, and source will always be grounded, and source and body will always be shorted. So what should be the potential at drain? Negative or positive? What is the diode here? Diode is this. What do you need? You need depletion region. If you need depletion region, that means you need to apply negative potential. So at drain you need to apply negative potential. So if you apply negative potential, what will happen? The depletion region will increase. What will be the direction? Direction of electric field will be this. The direction of electric field will be this. Why it will be this? Because here you are having negative and here you are having positive. So the direction of electric field will be this. This will be the direction of electric field, and there are holes available here. If there are holes available here, so in the direction of electric field, they will be swept away. So the holes are traveling like this. If the holes are traveling like this, that means what will be the direction of current? So the direction of current will be from source to drain, because the current direction is same as the direction of holes. The holes are traveling from source to drain. Because the electric field is this, that means in the direction of electric fields only holes travel. Do you know these things? The first thing is that electron travels in the opposite direction of electric field. Electron travels in the opposite direction of electric field. And the current direction is opposite to the motion of electrons. If electrons are traveling here, that means the current will be here. One more statement. Holes travel in the direction of electric field. If the electric field is this, that means hole will also travel here. And current flows in the direction of the motion of holes. If the holes are flowing here, that means the current will be here as well. So these statements we have understood in the first chapter only, basics of semiconductor physics, when we studied diode. So there we understood it. So just making you remember it. Okay. So if the holes are traveling from source to drain, that means the current will be from source to drain as well. So what will be the current direction? Current direction will be source to drain. Source to drain. Current direction is source to drain, right? Now what will happen if you keep on increasing the VDS value? If you keep on decreasing the VDS value, that means if you keep on increasing the negative supply, if drain is becoming more negative, what will happen? There will be more reverse bias. More reverse bias, that means more depletion region. More depletion region, that means current will increase. But at a certain negative value of VDS, the current saturates, because even though electric field is strong, but the channel will have lesser charge carriers. Because of that, the current saturates. Did you understand this point? Can you draw the graph now? What is the ID direction? ID direction is source to drain. Source to drain. What was the ID direction in N channel? In N channel, what was the ID direction? The electrons were moving from source to drain. So the direction would be drain to source. Whether it is P channel or N channel, always the charge carrier will move from source to drain. If the charge carrier are holes, that means if holes are moving from source to drain, that means the direction of current will be source to drain. If charge carriers are electrons, that means electrons are moving from source to drain, that means the direction of current will be from drain to source. Very easy, very straightforward. Here your VDS is negative and you are increasing the VDS value in negative direction. So your graph will be something like this. Say yes or no. You are increasing the VDS value in negative direction. So your graph will be something like this. And at some point it will saturate. Did you understand it? Right? It is the same as N channel depletion type MOSFET only. Okay. And since we are about to complete this depletion type MOSFET, so I want to tell you one thing, that depletion type MOSFET is not important that much. No one there is very rare chance that they will ask you question from depletion type MOSFET, because depletion type MOSFET are not used for amplification. I will tell you the reason why it is not used for amplification. But till now, can you guess why it is not used for amplification? Why depletion type MOSFET is not used for amplification? Can you guess? What did I say? We are designing an amplifier. In an amplifier, what did we say? That the current that we are having, that should be depending on the input voltage. That should be depending on the input controlling voltage. What is our controlling voltage? Gate. Gate is our controlling one. Tap. Gate is our controlling one. Even if I am not applying any gate voltage, when VG was 0, still there was some current. In the depletion type of MOSFET, the channel was already there. Because of that, even if I am applying VG, even if I am not applying any VG potential, VG is 0, I am not applying anything there. Even with the bias only, just with the bias, just with the drain potential, I am getting some current. And because of that, I will have some output. So your current is not depending on the VG value. Even if there is no VG, still you are having the current. And this is not what I want. I want my current to depend on the VG value. So that's why you can't use depletion type of MOSFET. Did you understand it? We will write it in later on, and I will explain you once more, but here only I explained it. So just now we are about to complete it, so that's why I am telling it. It's not that much of important, but to understand the now if you have understood the depletion type of MOSFET, the enhancement type of MOSFET will be a cakewalk for you. You will understand it very quickly. Otherwise, you would have got confused in enhancement type MOSFET. But now the path is crystal clear to you. What is depletion type and what will change in enhancement type, that we will see in next lecture. Okay, so this will be VD set. VDS set. Well and good. This is ID set. And what about this curve? ID versus VGS curve. So let's talk about VG. So what potential should I apply here? If I apply positive potential, what will happen? There are holes here. So because of this positive potential, they will be repelled. Or what you can think, if you are applying positive potential here, that means electrons will be coming here. From the negative side of battery, electrons will be coming here and they will be recombining with the holes. And if they are recombining with the holes, in the channel, there will be lesser charge carriers. And if there is lesser charge carriers, that means there will be lesser current. So if gate is positive, that means there is less current. And if I keep on increasing the positive voltage, that means if I keep on increasing the VG value, at some positive voltage, what will happen? The channel will be depleted of charge carriers and there will be very high electric field in this direction. There will be very high electric field in this direction. So if a hole comes here, it will follow this path because of this electric field. And if it is following this path because of this electric field, it will not reach through to the drain side and there will be no current. So at some positive potential of Vg, there will be no current in the transistor. Well and good, understood? Just the opposite of that. We don't need to write it all, just the opposite of that. So this will be Vp. So when the gate is positive, if you keep on increasing the positive potential, what will happen? The channel will have very less charge carriers. Also, there will be very high electric field from down to up, and because of that, the holes which are coming from source, they will not reach the drain side and there will be zero current, and that potential is known as pinch off voltage. This is the pinch off voltage. And if you increase it in negative direction, if you apply Vg to be negative, what will happen? This here there will be positive supply, so this positive supply will deliver holes. Some will recombine with this and some will reach to the channel. So some holes will reach to the channel and some will recombine, and those electrons, those holes will reach to the channel and our charge carriers will be more. If there is more charge carriers, that means there will be more current. That's it. Understood? So I'm not writing it all. I hope you have already understood because we have spent a lot of time in understanding N-channel depletion type MOSFET. This is just the opposite of that, nothing else. Right? So this is the N-channel, this is P-channel depletion type MOSFET. So if you increase the Vg in the negative direction, the current will increase. And what is the direction of current? Direction of current is from source to drain. Understood? All clear? So in this lecture, we have studied about depletion type of MOSFET. One more note will be there, that will be in depletion type of MOSFET. This I already explained, that in depletion type of MOSFET, the channel was already present. Even if I don't apply any potential at the gate, that means even if my VGS is 0, still there is some current. Look, here my VGS is 0, still there is some current. Even if my VGS is 0, there is some current. In the previous curve also we have seen, even if my VGS is 0, there is still some current. So my output current is not depending on the controlling voltage. This output current is not depending on the controlling voltage. Even if there is no controlling voltage, still there is some current. So that's why you can't use it as an amplifier, because as an amplifier, what did I need? I showed you. As an amplifier, what do I need? As an amplifier, I need a current which is depending on current or voltage, whatever it can be. I need a dependent source which is depending on my input, and which is not happening in our case. Understood? Although this R naught I should have shown in parallel, not in series. If I am making the current source, it should be in parallel. We will learn it. Here, this is a mistake. It should be in parallel. Yeah. So this requirement is not fulfilled by depletion type of MOSFET. So this requirement will be fulfilled by enhancement type of MOSFET, and how it will be fulfilled, that we will see in the next lecture. Okay, so this is written here, how it will be filled. So here there is no channel present. So we will have to make the channel by our own. By how? How we will make the channel? By applying the supply here. So now my current will be depending on the supply that I am giving to the gate. So my current will depend on that, and I will fulfill my requirement of an amplifier. So this question is a lot of time asked in the interview, that why you can't use depletion type of MOSFET for amplification and why you use enhancement type of MOSFET for amplification. So this is the reason. So in the next lecture, we will study about enhancement type of MOSFET. Okay, thank you.